Okay, let's start. Do you have any questions? Okay, so to continue with where we left off last time, right? So we were in the middle of chapter 4, and basically, the topics that we're concerned with, right, is the second order linear ODE, okay? Of course, constant coefficients. But the point is that it's not homogeneous. So non-zero right-hand side. All right. And so the model, right, that we have is AY double prime plus BY prime plus CY, okay, is equal to F of T. And the method that we want to use is the method of undetermined coefficients, undetermined coefficients basically it's just guessing the right form for different kind of F, okay? Picking the right form, okay, for different choices of F. All right. And also, of course, there's going to be, we will keep in mind the particular application that we have is for us, for me, is a spring mass system, but there could be the other, right, RLC circuit. The spring mass system is a case when we have A, B, C positive, okay? And in that case, A is the mass, B is the damping coefficient, and C is the K, okay, the spring constants. All right, so when we were discussing 4.1, the structure that we have is F of T is going to be some exponential function, e to the alpha t, for example. All right, and so here we just discussed, right, the choice of YP. Okay, so the choice of YP, the particular guess, right, is that so suppose that you have two distinct roots, right, for the characteristic function, characteristic equation, lambda 1 is not equal to lambda 2, all right, and it could be complex, who cares? And then here, right, the assumption is if alpha is not one of these, okay, the power or the coefficient, right, of the exponential term is not your lambda 1 or lambda 2, then basically the guess, right, is a constant e to alpha t, right? If somehow alpha is one of these guys, right, then the choice will be t, right? Like that, okay? And finally, if you have repeated roots, okay? So lambda 1 equals to lambda 2 equals to lambda. Then, okay, so, and then of course, if alpha is not equal to lambda, if alpha is not equal to lambda, then you have nothing to worry about. If alpha is not equal to lambda, then again, the particular choice of the guess is still e to alpha t. But if alpha, right, is equal to lambda, then because right here, the homogeneous solution, because right, the roots are repeated, is C1 e to lambda t plus C2 t e to lambda t, all right? That's the homogeneous solution. Then your YP, right, in this case, if alpha is equal to lambda, must be a t squared e to lambda t, all right, to begin with. And then finally, right, we mentioned the case that suppose, so this covers pretty much, right, all scenarios you can see when the forcing function is e to alpha t. But I just want to mention one last case, right, in the repeated root, if, right, the forcing function is t e to alpha t, all right? So this is an additional layer, right, of complexity compared to the usual forcing function that you would see in the textbook. If this is the case, and again, right, I'm talking about the scenario when alpha equals to lambda, all right? When alpha equals to lambda. Then here your guess must be, so first, right, it's going to be AT plus B e to alpha t. To address the fact that there's a t term here, you would match it with a general linear, okay, function like this. But then because the homogeneous solution is like this, all right, and alpha is equal to lambda, you must multiply with the smallest power of t to make none of the component here coincide with the homogeneous solution. In other words, you have to multiply with t squared. And that's, you know, the last part that I want to mention in terms of the different variations you can see in the case of the exponential forcing function. Question? Okay, so now moving on to 4.2, where, right, so again, we have ay double prime plus by prime plus cy equals to f of t. In 4.2, f of t will take the form cosine or sine. So it's going to be cosine of omega t or sine omega t, all right, for some omega. Yeah, the word always is very, very dangerous, right? There's nothing like always in math. The question is, what is the forcing function? Okay, what is the forcing function? Oh, and by the way, right, when you write t only, I think that's wrong to begin with, because even in the case of, right, in the case, let me see here. In the case where, you know, alpha equals to lambda, right, and in the repeated roots, you have to go with t squared to begin with, because your choice, right, without the square will be exactly this part of the homogeneous solution, right? So that's not possible. So the simplest case with the exponential forcing function with repeated root, right, is that you must go with t squared, right? If the forcing, you know, coefficient is equal to the root of the homogeneous solution, you know. So all in all, right, the principle is this, that you write down the form and then you multiply with the smallest power of t that would get you out of the homogeneous solution, whatever that is. Okay, so here, right, basically the principle says you start with this because that's the thing that would match with the forcing function. But then, right, this squarely match with this. Then you first try a t. Trying a t won't work because it will match with this. Then you try t squared. Okay, that's the principle. So same thing here, right? When I present a new forcing function, and that's why I was saying, like, depends on what kind of forcing function you have. So here's a forcing function. So first you match the form of the forcing function by doing this. This is purely just to match this. Then you see that, right, both of these components coincide with the homogeneous solution. Then, you know, I guess you try t, right? You try t, then this part gets out. But this, the b part, right, the b part still coincide with this. So you need everything, right, in your particular guess to not coincide with homogeneous solution, because anything that's part of the homogeneous solution will disappear. So it won't contribute to your guess, right? So t squared is the right one to work with. All right. Yeah, sure. Okay, and I mean, like, this sounds like a little bit cheesy, but the consequence of a wrong guess is that it won't work, okay? If you put a wrong guess here, when you plug into the ODE, it won't solve. You will see that things don't match up, all right? So I guess in terms of a test, you don't want that because that'll just waste your time. You rather land on the right guess, on the first guess. But if you have all the time in the world, if you guess a wrong guess, you can always go back and correct yourself. But that's painful. So if you rely on the principle and arrive at the right guess to begin with, it's going to be much more efficient. All right. So okay, here, right? So 4.2, forcing function is sine and cosine, all right? So let's look at an example just to demonstrate the point. Y double prime plus 2y prime plus 2y, right, is sine t, all right? So now, first, right, let's look at YH. So when we look at, right, the homogeneous, the characteristic equation, lambda squared plus 2 lambda plus 2 equal to 0. So lambda, right, plus 1 square is equal to minus 1. Or, right, lambda is minus 1 plus minus I. So your homogeneous solution is e to minus t, right? C1 cosine t plus C2 sine t. All right. Now, then of course we've seen this before. Nothing new. The new part, of course, is what is the particular form for YP. All right. So anyone care to make a guess in here with sine? What is the right guess? Exactly. Yeah, that is the right one, right? I was waiting for someone to just say something like only this, right? Only this won't work. And what Brad said, and I guess what Carl said too, right, is exactly right. That is going to be exactly this, okay? You could do this, and doesn't matter what, if you swap the order, right? But so this is the right guess, even though, right, the component only has one single sign, all right? There's only one single sign. You must use both, okay? You must use both, all right? What's the reason? The intuitive reason is this, right? That when you plug your particular guess in, it must be able to match up with the right-hand side perfectly, okay? Now, if you only guess sine, for example, then the derivative, right, the first derivative will give you a cosine term that you have no chance to correct because, right, it's the only one with cosine term. This is sine, and vice versa, right? So even from like a practical point of view, you must need both so that you have a chance to, balance the cosine and sine component because, right, the first derivative of sine is cosine and cosine is minus sine, so on and so forth. Okay, so that's the approach. Now, what I want to address here, right? So this works, okay, and then just plug in and solve for AB. This is fine, and actually, indeed, this is the approach that the textbook in 244 would use. Your textbook, right, does something slightly different, and it seems a little bit more efficient. So, and anyway, right, it's in your textbook, so I want to present this. By the way, I just want to emphasize, right, this approach perfectly works as long as you include A and B. All right, it doesn't change anything. But the text approach is like this. Basically, they go with the glorious name of complexification. I think that's too dramatic, but anyway, all right. So basically, it works on the it plays on the idea that, right, again, the Euler's formula, that e to the I t, right, is cosine t plus I sine t. Okay, so hold on. So this is just the idea, not the step. The idea, right, that they play on is this. But the step, okay, that they would do is like this. First, replace, okay, the right hand side, meaning whatever that is you have here, right, sine and cosine, with the corresponding with basically, let me just say this, with e to the I omega t. Okay, with e to I omega t. And why? Because, right, I mean, I guess the general form, right, is cosine of sine omega t. And so the complexification they're talking about is exactly, right, work with what is an idea two. Oh, this is a step, not an idea. The idea is only this. Basically, idea means where this thing comes from. This is the step. First, you do this. Yeah, okay. And of course, so in this case, right, what we do is just omega equals to 1, right? So it's just e to it. And then to solve, for the yp, right, as if, right, the right-hand side is an exponential forcing function. In other words, 4.1 technique. All right. What do I mean by as if? As if is because, this I is an imaginary, right, number. It has special meaning. But in step 2, you kind of ignore that and you just treat that as a symbol, like, whatever, like a coefficient. Okay. Step 3, though, is where but when you do this, all right, when you do this, your yp will have a real part, okay, and the imaginary part. Yes, because, basically, so I guess step 3 is to use Euler's formula to decompose your yp into this, because it's a complex number, right, by the structure of your guess. And finally, right, step 4 is that so how do I say this, right? This is the, it's not the fake IP, but more like in between IP. Okay, so this is what the real IP. All right, how do I want to say this? The IP that you would really use. Okay, let me say this. Maybe solve for y tilde. All right, so this is not the right solution. Okay, not the right YP. These are in between step. So RE means a real part, Lauren, and IM means the imaginary part. For example, when I write 3 plus 4i, then RE is 3 and IM is 4. Yeah, that's the standard notation to denote the two components of the complex number, right? So step 4 is the real YP, okay? Your YP will be the real part if the right-hand side, right, the forcing function is cosine. And it's going to be the imaginary part if the right-hand side is sine. Okay? We'll demonstrate this idea. So again, this may seem like complex, right? Complexification, whatever, in terms of the idea, but the cost of it is what? The benefit. The benefit is that when you do this, you only have to solve for one coefficient rather than two. So if for those of you who don't enjoy all this, complexification business, you can just proceed with this. All right. But I want to demonstrate maybe both approaches, right, and show you that they both land on the same solution. Okay, so going back to our example, y double prime plus 2y prime plus 2y, right, is going to be sine t. So I don't know. Let's do the a cosine y b sine approach, right? Approach 1, right? This is the straightforward one. Okay. So this will give you what? Yp prime is a cosine t minus b sine t double prime minus a sine t, right? Okay, so you line it up. Twice this guy, right? And then twice this guy, right? So you add them up. What do we get? If we add, all right, what's the sine term? Sine is minus a minus 2b, right? Plus 2a, so it's going to be a sine. And then the cosine will be minus b plus 2b. So that's b plus 2a, right? Is that okay? So that means a minus 2b is equal to 1. And 2a plus b is equal to 0, right? What would that give us? Let's see here. If I multiply everything by 2, right, and add, I got 4a is equal to 2, or a is 1/2, right? And then b equals to minus 1. Does that work? No, that doesn't work, right? Yeah, what did I do wrong? Oh, no, I need to multiply by 2 here, 2 at the bottom. So 2 is, a is 1, sorry, too quick, right? Let me see. If I multiply the bottom by 2, then I got 4a, right, plus 2b is equal to 0. Add them up, I got a to be 1/5, right? And b is minus 2/5. Would that work? Yeah, seems good, right? So the yp then, right, our yp is going to be what? 1/5 sine t minus 2/5 cosine t. Is that okay? Now let's see the complexification approach, okay? The complexification approach says that, right, because the right-hand side will be replaced with, right, basically you look at y double prime plus 2y prime plus 2y is e to it, okay? I mean pretending, right? So your yp will be a e to it. All right, this a may not have anything to do with the a above, all right? I mean, it's just a different notation for a different approach. So now you plug in, right? Yp prime is I, right, a e to it. Yp double prime is minus a e to it. Is that okay? So again, right, plug in, let me see here. There's a 2 here. There's a 2 here, right? So all in all, what do I get? I get minus a, right, plus 2. So a, right, times 1 plus 2i, right, is equal to 1. Are we okay? So a is 1 over 1 plus 2i. Is that okay? So what's our YP now? Our YP, right? Or rather, if you want, this is the tilde, right? It's the Y tilde P, not YP, right? Because this is the in between, right? This is not our real YP. It's going to be 1 over 1 plus 2I e to IT. Now, your task, right? So this is step 1 or step 2, I forgot, right here. Step 3 is to decompose it, right, in terms of the real part and the imaginary part. So what that means is you must write the first fraction as something, the second as cosine t plus I sine t. Does anyone know how to decompose the first fraction? Or not decompose, but convert the first fraction into a plus bi? What's the technique? How do I convert 1 over 1 plus 2i into a plus bi? Exactly, conjugate. So the conjugate will be 1 minus 2i over 5. Are you okay? Tell me if I'm moving too quick or too quickly, or this is fine. Okay, assuming that we're okay. Yep. So what are we looking for, right? We're looking for sine, right? Well, we have sine. So I mean, if you're lazy, you're just looking for what? You're looking for the imaginary part, okay? So you don't have to write down the whole thing. But YP then, right, is the imaginary part, which is what? The part that runs with the I, right? So the part that runs with the I will have minus 2/5 cosine. And then 1/5 sine. Are we okay? Any question? Is that the one that we got, Wolf? Yeah. So you pick, right? I don't care. I mean, either approach is good for me. I think both are fine, right? One stays just in a real, area and never mess around with the complex. One, kind of goes to the complex and it reduces the computation by 1, but the 1 comes from 1 plus 2i times 1 minus 2i, Lauren. So basically it's this, right? Yeah, I mean, the complexification approach is covered in the textbook. But as I show you, right, it's no different from this approach. So whichever you want. All right. So now what, I guess maybe I'm not sure the beauty of this or not, but you get something for free-ish, right? Suppose you were looking at y double prime plus 2y prime plus 2y is cosine of t. Then can you guess what yp is right away? What's yp is in this case? No. No, what are you talking about? It's cosine. Yp, right? What I mean is this, because you have done the work here. Not really flip, right? Flip-ish, but basically yp is the real part of this, right? It's a real part of this. So it will be 1/5 cosine t, and then plus 2/5, right, sine t, right? Just from reading this. So basically, when you do the complexification approach, you got two solutions for free. Well, you know, like, of course, you only have one forcing function, so you're not really looking for the other one. But that's I guess a bonus if you care to see it that way. I don't think so, right? Because there's a I and I is a -1, unless I'm wrong. Right? That's why I say it's not just flip, right? You got to pay attention to whatever the thing's saying. Are we okay? Question? All right, so maybe one more example, right? And we'll move on to other business. So another example is, let's say, question 2, okay? Problem 2 in 4.2, where is y double prime plus 3y prime plus 2y is 5 cosine of t. Is it too easy? You know what? Maybe not problem 2-ish. Let's just do something like this, right? 5 cosine of 2t. Just do, I don't know. All right. So I want to demonstrate, right? That doesn't have to be just cosine and sine t. So, okay, fine, right? Ignore the YH for now, okay? There would be an issue. You really need to check the YH too. Maybe let me just do the YH because I think that there's something there. So what's the YH? Lambda squared plus 3 lambda plus 2, right, is equal to 0. So I don't know what the factorization there is. Lambda is -3 plus minus square root of 9 minus 8, right, is 1. Wait, hold on. B squared minus 4ac. But this is real? Oh, so this is not complex even, yeah. Oh, so it does factor, sorry. So it's really, right, lambda plus 2, lambda plus 1 equal to 0, right? So it's not even complex. So YH is e to minus C1 e to minus 2t plus C2 e to minus t. All right. So what does complexification tell you, right? So complexification tells you that you want to do 5, right? E to the, what do I want to say here? 2it or I2t, I don't know. Is it okay? And so the guess, right? The guess will be yp, right? Y tilde p will be 5, oh, sorry, a, right? E to 2it. All right. And so plug in, right? Yp prime is 2i a e to 2it, and double prime is -4 a e to 2it. Okay. So if you plug in, what do you get? -4a, right, plus 2a is -2a, and then plus 2i, right, or plus 6i rather, is equal to 5. Is that okay? So a is 5 over -2 plus 6i. So I guess, right, here we might as well just convert that into, you know, a plus, the form, right, the usual form. So we multiply with minus 2 minus 6, right? So that would be, so, sorry, 4 plus 36 is 40. So you got 5 times minus 2 minus 6i, right, over 40. Right. And anything to simplify? Let's see. That would be divide by 5, right? You get 8 and divide by 2. So you got minus 1 minus 3i over 4. Is that okay? So now you put that in, right? So basically then y tilde p is minus 1 minus 3i over 4 times cosine of 2t plus I sine of 2t. Okay? And what do we want to pick? The real part or the imaginary part of this? You want to pick the real part, right? You want to pick the real part because the right hand side is cosine. So in other words, it will be minus 1/4 cosine of 2t and then plus 3/4 sine of 2t. Any question? Okay, so I think it's mundane, but I want to do the other approach too, right? So for two reasons. I want to double check that the two approaches give you the right solution, and second, right, give people who wants to do the other approach another chance to see, right, the other approach. So the other approach, right, is basically first you have the same thing. So approach 2, right? This is approach 1. Approach 2 is, so this is 5 cosine of 2t, right? Approach 2 is basically say yp is a cosine 2t plus b sine 2t, right? And then differentiating plug in. So yp prime is minus 2a sine 2t plus 2b cosine 2t. Yp double prime is minus 4a cosine of 2t minus 4b sine 2t. All right. If you plug in, right, then you have something cosine and something sine, right? And that's supposed to be 5. So what's the something cosine? Well, you got minus 4a here, plus a is minus 3a, and then plus 2b. Okay. And then on the other hand, for the sine, you got minus 4b plus b, so minus 3b, and then minus 2a. Okay. So the system that you are looking at is minus 3a plus 2b is equal to 5, and minus 2a minus 3b is equal to 0. So, okay, if you multiply the first one by 3 and the second one by 2, I run into trouble, right? Because here I got 13a is minus 15 over 13. That's not what I got from the previous one. Ooh, yeah, thank you, Carl. What the heck am I doing? So silly. Thank you, thank you. All right. 2, 2, 2. Thank you, thank you. What am I doing? Yeah. And then let's do 3, right? 3, which is minus 6. And then 6. Yeah, and I hope maybe, right, this advertised for the other approach, because I don't run into this kind of system, right, with the other approach. Anyway, right, so, okay, fine. So now if I plug in, what do I get? All right, so minus 4a plus 2a is minus 2a, and then 6b, okay? And the other one will be minus 2b, and then minus 6a, right? So minus 2a plus 6b is equal to 5, minus 6a, and minus 2b is equal to 0. So I need to multiply the first equation by, I keep the first equation, I multiply the second one by 3. So minus 2a plus 6b is equal to 5, and then minus 18a minus 6b is equal to 0. So minus 20a is equal to 5, or a is minus 1/4, right? And that would make b equals to what? So the second one say, right, that basically if you divide by 3, you got b is equal to minus 3a, so b is 3/4. So yp is, what do I have here? A cosine, right? So minus 1/4 cosine 2t plus 3/4 sine 2t. Is that what we get above? Yeah, right here. Okay. So again, take your pick, right? If you feel like one of the approaches is too painful, do the other. But I do see that they kind of have both their pluses and minuses. Any question? All right. So then that's how you solve it in general, right? For the YP. And of course, the general solution is YH plus YP, right? I don't have to repeat that. Now, the next thing I want to talk about is how to, it's a technical thing, but it's relevant, that writing or expressing YP as a single cosine function. Okay. So in other words, this is technical, but it has a meaning. So when you look at, let's say, a generic system, let's say, I don't know, something, right? Let's say A, or let's say a constant K, cosine omega t. All right. Then you know, right, that the YP will be A cosine omega t, right? Let me do this. Maybe let me call it K1 and K2 because I want to reserve A for something else. Sine omega t. Okay, like this, right? That's the structure of the YP. Now what you want to do is to express this as a single function. You want to write this as, give me a moment. I think you want to express this as A cosine of omega t plus phi. All right. So basically, you want to convert this form into this form. So then your general solution, right, will look like something like this. Y of t will be YH, whatever that is, and then plus A cosine omega t plus phi. Okay, because basically this has a more meaningful interpretation. So first of all, I mean, we'll go into the interpretation later on. Any question on this, for example, on the goal of what we want to do? All right. So what's the what's the point of doing this, right? So the reason is this, that motivation, okay? So it's not just for mathematical purposes. It really has a easier physical interpretation. That basically, you know, when A, B, C are positive, okay, again, think of the spring mass system. Do you remember what happens to the YH when t goes to infinity? So in the presence, right, of damping coefficient, doesn't matter whichever case it is, under damping, critical damping, over damping, the YH always goes to 0. Okay? So basically, as time goes on, right, with a forcing function like this, your solution will converge to the steady state solution of this form. And so, you know, when you have something like this, it's better to convert it into this because A will represent the amplitude of your long-term state solution. Well, K1 and K2, right, even though it expresses that, is not as neat. And phi, right, basically is the phase angle, the phase shift, right? How kind of away from the origin, right, is the steady state solution positioned. All right. So in this case, the limit as t goes to infinity of your solution will be yp. And so A will be the amplitude, right? So this will be the steady state solution. And phi is called the phase angle. Okay. So then that's the motivation on why we want to compactly rewrite this into one single form. Now, of course, then goes the technical question of how to do so. All right. So how to find, right, A and phi, right, in terms of K1, K2, and omega. So basically, it's about equating coefficient and remembering your trig identity. So you have K1 cosine omega t plus K2 sine omega t is A cosine omega t plus phi. Okay. So you want to expand this. You want to expand this, right? So you want to expand using the cosine, sum of cosine term. So something like this, let's say. Okay. Does anyone remember what this is? It will be cosine of theta 1 cosine of theta 2 minus sine of theta 1 sine of theta 2. All right. And so expanding, right, the right-hand side gives you A, right, cosine omega t cosine of phi, right, minus sine omega t sine of phi. So what do you have? You have something like, hold on. Actually, apologize. I think for some technical reason, I start to remember now that the phi here is expressed as a minus rather than a plus. Okay, I think that the phi here is expressed as a minus rather than a plus. I remember now. It will match up nicely down here. So like this, minus. Okay. And so the formula that we were looking at is minus here. And the cos of that is going to be a plus. Okay. But so the right-hand side will become a plus, which allow us to say that K1 is A cosine of phi, and K2 is Ka sine of phi. Is that okay? So what does this remind you of? It should remind you of polar coordinate, right? Where basically, right, A, right, A square is K1 square plus K2 square. And then, right, tangent of phi is going to be K2 over K1. All right. Now, if you want to decide beyond this, like for example, the sine of A and that kind of thing, you have to go back to this and decide what the phi angle is. All right. And I think the convention is the angle phi is between 0 and pi, if I'm not mistaken. And so that will help you decide what the angle phi is in this case by this ratio. And then you can decide what cosine phi is to decide what the sine of A is. Okay. Any question on this? All right. So unfortunately, I don't think we can say much more beyond this kind of relation in terms of particular numbers, because you have to like figure out what the actual values of these are, even in terms of simple examples. So let's not draw into this. But when you read the book, right, there will be a part of discussion where the expression on the y on the particular solution, right, takes on this form, and it becomes relevant because of this kind of technique. Okay. All right. So if there's no question, let's move on to 4.3. And this is undamped forcing. And resonance. Okay. And so here we're looking at so basically the equation, right, is undamped forcing. So we're looking at something like what my double prime plus ky is equal to, let's say, a cosine omega t. All right. And so the damping coefficient b is equal to 0. All right. So for example, let's take a look at y double prime plus 2y is cosine omega t. The thing we want to study here is the change in the behavior of the solution for different values of omega. Okay. So first of all, this is valuable in of itself like this in terms of math. So when you look at the homogeneous solution, you got lambda squared plus 2 lambda is equal to 0. Plus 2, right, is equal to 0. So lambda is plus minus square root of 2i. So yh, right, is cosine of square root of 2t c1 plus c2 sine of square root of 2t. Okay. So question, right? Suppose that you have y double prime plus 2y, let's say, is cosine of t. Then what is the guess for yp in this case? Compare with this. Yp double prime plus 2y is cosine of square root of 2t. Then what's the guess for the yp? Anyone? What's the difference between these two? Right, but what's the form, right? What's the form of the solution in each of this? So the form of the solution in the top one would be a cosine of t plus b sine of t. The form of the solution on the second one would be a cosine of square root of t plus b sine of square root of t, square root of 2t. What do we mean by that? What do you mean by frequency difference? So just this then, this is the right form. No, absolutely not. Because if you plug this into this equation, what do you get on the left-hand side? If you plug this into here, what do you get? You will get 0, because that's exactly YH. Okay. So the difference is at for the second one, you need a t in front of it. You need a t in front of it. Okay. So you see, the point is, right, that the critical value of omega in this case is square root of 2. Okay. And so we want to, because at square root of 2, this is the form of the solution. And we want to investigate, right? We want to see how the solutions, how the solutions behaves for, I guess, omega far away from square root of 2, omega close to square root of 2, and 3 omega equals to square root of 2. And exactly is omega equal to square root of 2 is called the resonance, the case of resonance. Okay. So first of all, any question on the choice of the YP in this case? It follows the principle of, right, if your choice, if your guess coincide with the homogeneous solution, you must multiply by a factor of, the lowest power of t to get you out of it. And here, right, exactly because the frequency here, right, coincide with the frequency, the natural frequency of the system, then you must multiply with a t to get it out. And that changed the behavior of the solution in general. Okay. So maybe let me demonstrate just in terms of the math. Yeah, okay, good question, right? I mean, that part is vague, and I would say close is gonna be maybe around 0.01 or 0.1 away. And what do I mean by this? Qualitatively, one, basically there's nothing, okay? There's nothing unusual about the kind of solution. 2 is the phenomenon of what we want to call beat. And 3 is what we want to call resonance. So to answer your question, how close is close? Close enough so we start to see the beat in terms of our solution. And then when you're exactly at the natural frequency, then you see resonance. Okay, so yeah, however close that is, so we see the beat. All right, then that's the point. Yeah. So, all right, so maybe there are several things, right, to address. There's the math part, which is to find, right, the particular solution. Exactly. There's a physics part, or, I don't know, the model part, where I want to explain, right, the beat phenomenon and resonance phenomenon, okay? So we need to address each of these separately. I will address this first, right? And then maybe spend more time on this next class, or start discussing this in this class. Okay. So maybe let me show you, right? Some of you may have already seen this kind of picture, but some of you may not. So let's see, let's show you what I mean by this kind of phenomenon. Hold on. Sorry. So all right, so here. So in terms of Nigel's question, right, this is what we think of as far. Like not much going on in terms of the solution that we can recognize about. This is what we think of as close, because you start to see the solution forming this kind of beat behavior. Okay. So something like this, for example, is probably close enough. All right. And so what is beat? Beat is basically, you see there's going to be a rhythm in terms of the amplitude of the solution. Okay, in terms of the max amplitude of the solution. The solution, right, oscillate like this, okay, the blue line. But there's an envelope, there's an outside envelope that you can start to see a pattern of a long-term, right, long period sine curve, okay? So this is what we mean by close to the natural frequency. But when you're exactly at the natural frequency, then this happens, and this is resonance, meaning your solution just gonna increase according to a T envelope, and so it's gonna blow up as time goes on, and like basically the swing is gonna be out of whack and gonna break your system. Okay, that's the phenomenon that we want to describe, right, mathematically, and see how that translates to this picture. I guess this picture is clear. Okay, if you see the math. The beat is a little bit more subtle to see. All right, and then of course, when things are normal, this is what I mean, not normal, but far away is what this picture is demonstrating. Any question on this? Okay, so maybe let's just address the YP part first. Okay, so the finding YP. Okay. When the frequency, okay, of the forcing function coincides with the natural frequency of the system. Okay. So again, right, that basically what you have is, let me just do make it easier. Let's say y double prime plus y, okay? And case one is going to be, let's say, cosine of 2t. And case two is going to be cosine of t. All right. So in both cases, right, you see that the YH is cosine of t plus C1 cosine of t plus C2 sine of t. All right. The YP, the guess of YP in the first one, because the frequency here, right, or the term here is 2, is not the same as the 1 in the natural, so the frequency, right, of the system. So by natural frequency, what I mean is the coefficient of the cosine and sine of the homogeneous solution. Okay, I mean, it's technically not exactly a natural frequency, but it's related. So what we mean is this coefficient is not the same as this coefficient. Then YP will be A cosine of 2t plus B sine 2t. And then you plug in and solve. But when here, right, because cosine of t is exactly coincide with this part, then your YP, your guess, must be A, right, cosine of t plus B sine t, but with a t in front. Okay. So, I mean, let's plug in and solve for each of the case here. So for the first case, right, if you want to solve for A and B, actually, I think it's boring. Do you want me to demonstrate how to solve for A and B in each of the case? Or you understand the principle and you can solve it for yourself? Indifferent? Doesn't matter? Yeah, just plug in. But the point is, I want to emphasize that if you guess the wrong form here, you will get nothing. But this is the right form. If you plug in, you will get it. I just don't know if you want to sit here and see me plug in and solve for all these things to show you that it's right. Like, are you convinced that it's right, or you want me to show you? It's good. I hope, I trust. Okay, so let me make one case, right? Is this? What if, right? Suppose I have a homogeneous solution. Let me see if I can come up with. Let's say this, right? Let's go with the previous example we had, where what if we have y double prime plus 2y prime, right? Plus 2y is cosine of t. Okay. So here, right, remember this is the example we looked at before. So YH is e to the minus t C1 cosine t plus C2 sine t. Okay. What is, so here, is this the case where the frequency of the forcing function coincide with the natural frequency of the system. Is this one of those cases? In other words, what's the guess of the YP here? Is it this? Or is it this? Which one is it? With or without the T? Okay, so let me ask you an intuitive physical question, right? In terms of physics, what's the difference between these two cases in terms of model? What's the difference between these two cases? Right. The second one has damping. Now, do you agree that this case is exactly resonance, right? Because you are forcing the system to oscillate in the same way as the natural, right, the natural frequency of the system, so it's going to oscillate wider and wider. When you do that, let's say with the system that's damped, do you think you will achieve resonance? Well, resonance is long term, right? That's so that's nothing like long term or short term here either. So what does resonance means? Resonance means that the amplitude, right, of the oscillation goes to infinity as t goes to infinity. I'm asking, you know, you guys who done physics or engineering, right? I think any damping, just a little bit. Meaning what? So I'm asking a very, very simple question. Is there resonance or not? Right. There's not gonna be resonance, right? Now I have to admit, I do not know that clearly, confidently from physics, but the math definitely says that this is the solution. So that's why I'm sure too that in physics that there's no resonance when any damping presence, no matter how small, right? It's kind of okay. I guess, you know, in reality, I guess I don't know how things might break or whatever, but why? The point is this, right? The true root here is not just cosine, but it's going to be minus. That's a real part plus. So basically, the root of the solution here is lambda is -1 plus minus I. Okay. While if you consider, right, complexification here, if you want, that is e to it. The I here and the -1 plus minus I have no coincidence. Therefore, your guess is purely cosine sine. There's no t. There's no coincidence that forces you to multiply with the t mathematically. So therefore, you know, there's no resonance as long as you have any kind of damping. Therefore, right, the title of 4.3 is undamped, you know, oscillation, undamped forcing and resonance, right? With damping, you won't achieve that. Okay. I mean, maybe there's some interesting phenomenon going on if you pick this like this, but as far as damping is concerned, no, your solution will not blow up as t goes to infinity. Okay. So mathematically, what I want to emphasize is what? As long as there's a middle term, okay? As long as there's a middle term, then the coincidence between this and this is not what you should consider because there's an exponential term outside. So the guess is still this. But if there's no middle term, right, then there could be a danger of coincidence between your homogeneous solution and your guess. And so you may need a t if this and this coincide. Is that okay? question. All right, so I think this is a good place to stop, right? In the next class, we're going to go into the physics and describe how the beat and the resonance happens. Yep, thank you. You too. Thank you. Yeah. Okay, one second. Let me stop recording and then